Oh, this is the fourth part of the mini course on homological stability by Sander Kupers.
Okay, thanks for everyone who showed up for the last talk. So today I'm going to give a bit of an outlook on some other phenomena related to homological stability, but not equal to it. So what I'll talk about in this lecture is representation stability, and higher order stability. And what I'll do in both cases is work through a particular illustrative example. And I will not try to explain how you prove these statements or even what the general theory is, just because there's really not enough time for that. There are a few other topics that might be of interest, which I won't talk about today. One is about stability near the top dimension. If you think of H0 as being the bottom dimension, some groups satisfy a type of Poincare duality, in particular have a well-defined top dimension, or at least virtually do. And you could ask about stability phenomena there. So I won't talk about those because they're harder to formulate, and because one of the examples that was conjectured to have this type of stability turned out not to have this property. Another thing I won't talk about is something called stable stability, which is a phenomenon modelized space of manifolds, where once you've stabilized by one type of manifold, if you stabilize by another manifold, it's sometimes an isomorphism homology. But these we won't talk about. That's a very specialized topic. But it may exist in other cases as well, so I think it's worth mentioning so people know that something like this exists. Okay. So we'll start with representation stability. And to introduce this, I want to look at a close cousin of the classifying space of symmetric groups, which are the unordered configuration spaces. Okay, so let's give the definition for just a general topological space X, which eventually will become a Euclidean space, or more generally a manifold, but the definitions make sense more generally. Okay. So the configuration space of an unordered points in X will denote by Cn of X, and it will be given by n tuples of distinct elements up to the action of the symmetric group, which permutes them. Okay, so by construction, this is a quotient of another space. Namely the ordered configuration, or the configuration space of n ordered points in X, which I'll call conv n of X. So that's just the first part of the expression. You see at the top of the screen, where I don't take the quotient. By the symmetric group. Okay. So one reason we're introducing this is so that I can explain the relationship between the configuration space of unordered points and symmetric groups. What we'll use is the following lemma. So it will say that this configuration space of ordered points in a d-dimensional Euclidean space is d minus 2 connected. And from that, it will follow that there is a d minus 1 connected map from the configuration space of unordered points to the classifying space of the n-symmetric group. So the second is an easy consequence of the first, because the action of the symmetric group on this configuration space is free, probably discontinuous. So the quotient is a homotopy quotient, and all we're doing is replacing this highly connected space by a point. Okay, so I'm going to focus on proving the first statement. And to do that, it's easy to prove. It's better to prove a more general statement. So instead, I'll prove that if I take this configuration space, and I remove some points from it, I want to prove that this is d minus 2 connected. Of course, the case k is 0 is going to give it what we want. Okay, so it will be a simultaneous induction over n and k. Okay, so what's the first case? The first case is when n is 1. So we have 1 point. In the Euclidean space, minus k points. Well, that is just homeomorphic, maybe even equal to this space. And that's easily seen to be homotopy equivalent to a wedge of spheres. Right, it's this picture where, like, if you remove R2, and you remove 2 points from it, you deformation retract onto a wedge of 2 circles. Okay, so how do you get from the case n to the case n plus 1? Well, you use it as a fibration. Let me write it here so I have space to write the fiber. Given by just remembering the location of the first point. So that this fibration was proven by Vidal and Neuwirth. And what's the fiber? Well, the fiber is all places where you can put this, the remaining n minus 1 points. So I guess I'm doing the induction from n minus 1 to n. That's the fiber. And we know that this side is d minus 2 connected by induction. And we know that this side is d minus 2 connected. Previous argument. So the same has to be true for the middle term. So as a consequence of the second part of this lemma, there will be homological stability at least in a range for configuration spaces of n-ordered points. You see these maps to the classifying space of symmetric groups that are d-1 connected. They fit into a homotopy commutative diagram. Like this, where the subtlety is defining what this stabilization map is on top. So let me draw a picture that you can then think about how to make precise. If I have, say, 5 points in the Euclidean space, and I want to stabilize, what I can do is add a new point far away, say on the right. Now, to really make this precise, I probably have to push the original particles in a little bit to make space, but you can try and write down the formula for it. Okay, so this diagram commutes. So as a consequence, you would get homological stability for the sequence C0 to C. I guess D needs to be at least 1 for this map to be defined. And the way we've proven it, you would get it only in degrees star smaller than d-1. But in fact, it's true all the time. So there's plenty of different arguments that remove this restriction and say that these spaces exhibit homological stability. It's also true that all the stabilization maps are injective, which is proven in the same way as for symmetric groups. So that's an exercise. Okay, so the configuration space of unordered particles in Euclidean space, they satisfy homological stability. What about configuration space of ordered particles in Euclidean space? Do these also satisfy homological stability? And the answer is no. Because we can compute explicitly what the, let's say, rational homology of the nth configuration space RD is in the lowest degree in which it can be non-zero, except, I guess, degree 0. What is this isomorphic to? It's n-1 copies of the rationals. So if you fix the degree and let n vary, we never get a stable value. Explicitly, these are generated by particles moving around each other. It's groups generated by those representatives. Now, to understand better what's going on, it's helpful to remember that the symmetric group acts on this homology group because it acts on the space, right? That's how we constructed the configuration space of unordered particles. So it acts on this collection, on this vector space, and it's probably helpful to try and understand what it is as a representation of the symmetric group. So as a rational, as a Q sigma n module, so a rational representation of the symmetric group, it is equal to, you take the regular representation, so the free vector space on set of n elements. This has a map to Q, which is as a trivial representation, which is the augmentation map. And you take the kernel of that. In other words, this is called the reduced regular representation. Okay, so when we take into account the group action that's naturally present on this space, then this homology group does admit a uniform description for n sufficiently large, in this case, in fact, for all n. So as a representation, it does stabilize. Now, let's make this into a precise statement, because so far I've just somehow given a name to it that's uniform. But somehow this philosophy, there's many different ways of making it precise, is called representation stability. Okay, so to give a more precise statement, let's replace Euclidean space by a manifold, just because it's more interesting that way. Of dimension d at least 2. And let's assume that it's connected and of finite type, which means homotopy equivalent to a finite stability complex. Okay, so to give the statement of representation stability for the rational cohomology of ordered configuration spaces of this manifold, I need to make more precise by what I mean by a uniform description of these representations. So the precise statement will need, at least the one I'm giving now, needs the classification of finite dimensional representations of the symmetric group over the rationals. Okay, so these, the irreducibles, so it's semi-simple, everything splits as a direct sum of irreducibles. And the irreducibles are in bijection with one of two equivalent types of combinatorial objects, either Young diagrams with n boxes, or equivalently partitions of the integer n into positive integers. So let's use the latter description. And give some examples. So the trivial representation, that corresponds to the partition writing the number n as just n. And this reduced regular representation corresponds to writing n as the sum of n minus 1, 1. Okay. The point of introducing this is that I can stabilize these partitions in a formal manner So my partitions are lists of numbers that you're supposed to sum together to get n. And they will always be ordered so that the first one is the largest. And so you can stabilize these by adding 1 to the first entry. It's possible that some entries are the same, so there could be multiple largest ones. Okay. So in that sense, I can take isomorphism classes of rational sigma n representations, I can take these isomorphism classes to isomorphism classes of rational sigma n plus 1 representations by stabilizing the corresponding partition. Okay. So when you have a sequence of representations of sigma n for all n greater than or equal to 0, you can ask whether the multiplicity of a partition that looks like, let's say, I1 plus, well, let's start with a partition of some number n, and then look at the sequence of stabilized partitions. We can ask whether the multiplicity of these guys stabilizes. And if that's true, then you say that there's maybe multiplicity stability. So that's one way, maybe the most elementary way of making representation stability precise. You give consistent names to all the isomorphism classes of representations that occur, and you ask whether the multiplicities of these stabilize as n goes to infinity. And so the theorem is that for m as above, so at least two-dimensional finite type connected, this is due to Tom Church. If you look at the cohomology, in fixed degree, you get a sequence of representations of the symmetric group. These exhibit multiplicity stability. Now, I could have formulated this for homology as well by using the universal coefficient theorem and the fact that a dual of a rational representation of symmetric group is isomorphic to itself. But there's a reason to prefer phrasing it in terms of cohomology. Maybe a remark. Well, I didn't say that my manifold was open, so I don't have a stabilization map which brings in a point far away, like we had for the Euclidean spaces. Rather, in this case, we have forgetful maps. You see, what you can define on the configuration space of ordered points is a map which deletes or forgets the ith point. This doesn't make sense for the unordered ones because there is no ith point. You've quotiented out by the ordering, or by the symmetric group changing the ordering. But here it does make sense. And on cohomology, we get maps going the other way. Which, first of all, maybe more resemble the stabilization maps you're used to, which increase the number of particles. But it also turns out that the algebraic structure I'll talk about in a second is better behaved when you look at the maps going this way. Okay, so what is this algebraic structure I just mentioned? This very elementary approach to representation stability is difficult to generalize to other sequences of groups or more complicated coefficients than rationals, because often there is no classification of all representations, and it's not possible to give them consistent names in terms of partitions. I mean, this even occurs when you look at configuration spaces, but look at their cohomology with integral coefficients rather than rational coefficients. So to deal with that, you rather study the representation theory of certain categories. And I'm going to tell you a little bit about that because a lot of representation stability, I mean, it's not so different in terms of the topology in comparison to homological stability. However, it is quite different in terms of the algebra that you have to do. So I want to give a bit of a flavor of the type of algebra that gets involved, which is categorical representation theory. Okay, so what is the idea in the case of ordered configuration spaces? So the observation that you make is that these rational cohomology groups of the configuration spaces plus these forgetful maps that I just mentioned, these assemble to a functor out of a certain category, which is, let's do it, Z coefficients, which is exactly the category of finite sets and injections. Okay, for each finite set, you get maybe the configuration space of points labeled by the finite set S in M. And whenever you have an injection, oh, sorry, it goes. Whenever you have an injection, you restrict to only these particles. So let's see, if you have a T sitting inside of S, you naturally get a map from the configuration space. Sorry, I made a mistake. There's no up there. Sorry for the confusion. So there's a map on configuration spaces which forgets all the points that are not in the image of this injection. And then when you take cohomology, you get back a map going the usual way. Okay. So let's call these types of functors let's call them Fi modules. The idea being that in this case, there's a category of finite sets and injections that's replacing looking at each of the individual groups. And just like we were looking at sigma n modules before, now we're looking at Fi modules. And one way of rephrasing representation stability in a way that makes sense also for integral coefficients is to say that these are finely generated Fi modules. And so if you want to prove a result like this, it's helpful to have a good understanding of the category of Fi modules. For example, to know that it's Noetherian. Okay, so that's, and a lot of papers in this field end up also proving these types of categorical representation theory results. Okay, so this is, it's a theorem of Church, Ellenberg, and Farb that the cohomology of configuration spaces of a manifold that's before with integral coefficients is a finely generated Fi module. Okay. So maybe it's good to just connect this back to what we talked about before. We talked about ordinary homological stability. So it fits in a similar framework, but it's just quite degenerate. So ordinary homological stability is representation stability where you replace this category Fi with the post set of natural numbers ordered by less than or equal. Okay. And then you make the following observation. If you have a sequence, sorry, if you have a functor from the natural numbers to abelian groups, if you read what the definition of being finely generated is for such a functor, this is true if and only if you're eventually constant. So in some sense, ordinary homological stability is representation stability with this very degenerate category you're working with. It's like working with ZX modules. Okay. So in the lecture notes, I've included a lot of literature, reference literature about representation stability if you want to learn more about this. Okay, so that's one of the two stability phenomena I wanted to talk about. Are there any questions about it? If not, then I'll continue with higher order homological stability. And in this case, the illustrative example I want to talk about is that of mapping class groups. Okay. So let's take a surface of genus G with one boundary component. Then we can look at the diffeomorphisms of this surface that fix the boundary pointwise. And are topologized in the smooth topology. And then we can look at the group of path components. And that's what, by definition, the mapping class group is. It turns out there's really no loss in passing to the group of path components, since the path components of these diffeomorphism groups are contractible. So from the point of view of homotopy theory, you might as well just look at these mapping class groups. Okay. So we could look at the classifying spaces, these groups, and see what we can say about them. For example, can we compute their homology or cohomology? This is of interest because this is equivalent to the algebra geometric modelized space of genus G curves with one marked point with tangent vector. And I guess you have to interpret modelized space here in the right way. Otherwise, it's just a rational equivalence. Non-zero tangent vector. The point is, if you add a boundary, you're no longer algebraic. So replacing a boundary with a marked point and a non-zero tangent vector is like an algebraic version of having a boundary component. Okay. So people have been interested in these modelized spaces for a long time, and hence also in the classifying spaces of these groups. Now, whenever you have one of these surfaces, I can take the boundary connected sum with the surface of genus 1. Okay. And whenever I have a diffeomorphism of this first surface, that's the identity on the boundary, I can extend it by the identity to the new piece. That gives me a homomorphism between these groups, and hence a map on classifying spaces. Okay. And something that you can find in the lecture notes for the previous talk, but something that I didn't mention, is that this sequence of groups that I get by varying G exhibits homological stability. So the induced map on homology this is a surjection in degrees 2g/3, then isomorphism slightly lower degrees. As you might have realized, 2/3 is not of the form 1/k. So this homological stability result, at least with this range, can't be deduced from the general result we talked about last time. The best that can do is a slope 1/2 result. So this requires some extra tricks to get a slightly better range. Okay. Now, implicit in that statement is the following claim. The claim that I can apply that theorem to the sequence of groups, which in particular means that they fit together into a braided monoidal groupoid. So let me I will give a geometric instantation of that later. Okay. So what this result says informally is that the homology in fixed degree is eventually constant. And if I invoke some kind of calculus-based analogy, I could maybe say that it eventually has vanishing first derivative. And what higher order stability is in this analogy is the vanishing of the derivative of the derivative, etc. Okay, that's maybe a vague analogy of the type of phenomena I want to talk about. So let's make this into a precise statement. So what might play the role of the first derivative of the homology? Well, I think it should probably be the relative homology groups of the stabilization maps. Right? By the long exact sequence for the homology of a pair, these vanish if and only if the stabilization maps are isomorphisms at the very edge of the vanishing in a gaseous surjection. So higher order stability will be that, okay, maybe second order stability is that the statement eventually have a vanishing second derivative, or maybe equivalently, eventually have a constant first derivative. So it should be some kind of homological stability result for these relative homology groups. And in some sense, that's really boring because these groups are eventually zero. So in some sense, they like have stability. But of course, the interesting secondary stability results are when these groups are not zero. So you're programming into some kind of metastable range before stability kicks in. And just like you need stabilization maps to be able to talk about homological stability, here you need secondary stability maps to be able to talk about secondary stability. And part of the game is constructing those maps. So I'm just going to say that these exist. And as you'll see, they're probably going to be trickier to construct because these maps will not be unique, provably non-unique, and they will change both degree and genus. They'll change the degree by 2 and the genus by 3. Okay. And then the theorem is that these are surjections isomorphisms in a larger range than the range in which these groups are zero. This is something that I proved with Sir Iglesias and Oscar Randall Williams a couple of years back. So phi star is a surjection for any choice. Stabilization map for degrees less than or equal to 3g/4 and an isomorphism in a slightly lower range. Okay, I mean, the crucial observation here makes this interesting is that the number 2/3 is smaller than the number 3/4. Okay. So not that many results of this nature are currently known. I've listed all the references that I'm aware of in the lecture notes, and the only other examples, apart from mapping class groups, are general linear groups of fields, or local rings maybe, and configuration spaces. But in principle, I think it should exist in nearly, this type of result should be true in nearly all of the examples where homological stability is known to hold. However, sometimes it might take the following form. Maybe a result of this type is true, but you can prove at the same time that this phi star is 0. And if that's true, the 0 map is an isomorphism. That must have been the case that the groups were 0. And so you just get a better homological stability range. So sometimes this type of secondary or maybe even higher order stability result might manifest itself as an improved range. Okay, so in the last 13 minutes, I want to give some sense of the strategy or the ingredients for proving a result like this. Because it uses somewhat high-powered homotopy theory. Okay. So the crucial observation is that whenever G is a braided monoidal groupoid, if you take the classifying space of the nerve, I get something called an E2 algebra. So what's an E2 algebra? Well, there's an entire spectrum in homotopy theory of increasingly commutative algebraic structures, where E1 means being coherently associative, and E infinity means being coherently commutative. And an EK algebra for K between 2 and infinity is something in between, where the space of multiplications that you have becomes increasingly highly connected. So maybe on the spectrum, somewhere over here, we have E2. Somewhere near the beginning of the spectrum. Now, what is the official definition of this? The official definition uses the notion of an operand, which is a gadget that encodes algebraic structures with n-ary operations for all n greater than or equal to 0. And I'm going to write down what it is in this case. So E2 is an operand whose space of n-ary operations is given by, let me say, rectilinear embeddings of n copies of D2 into D2 with disjoint image. So in other words, it's the collection of some small disks. These disks are only scaled and translated and have to be disjoint. So this would be an element of E2, 3. And the idea is that these spaces encode n-ary operations in the sense that in E2 algebra, it should have, it involves the data of maps like this. Whenever you have an element of the space of n-ary operations and n elements of your algebra, you ought to be able to produce a new element of your algebra. Okay, and I'm leaving out lots of like axioms that need to be satisfied and even some data that needs to exist here. That's just because there's not enough time to go into detail. Okay, so how are the mapping class groups, the classifying spaces, how can those be made into an E2 algebra? Now, I won't give you the details, which are in an exercise, but here's the idea. The idea is that if you are given an element of the space of n-ary operations of E2 operand, and you're given some diffeomorphisms of some surfaces, so these are surfaces of genus GI, and they come with diffeomorphisms that are the identity on the boundary, then you can get a diffeomorphism of this larger surface by extending them by the identity. So that's not really a precise description, but that's roughly the idea why the E2 algebra structure, where it might come from. Okay, so this is some kind of algebraic structure that's of a homotopy theoretic nature that's present on the disjoint union of these classifying spaces. Now, what the usual homological stability argument now does is that it extracts from this the multiplication by a fixed element of BG11, together with the fact that this is somewhat commutative. But maybe it's fruitful to use this entire algebraic structure that's around. And that's really necessary to prove these higher order stability results. Okay, so I'm just going to give you the barest outline of how it's used, but maybe you'll see where some interesting homotopy theory is going to come in. Okay. So what's the strategy? So the strategy is to try to build a custom E2 algebra A, which approximates the one we're interested in. Now, what I mean by approximate is something relevant to the situation at hand. I mean that it captures the homological stability phenomena in a range. So it won't actually be a good approximation in the sense that it's going to have the same homology or something. It's just going to have the same homological stability or secondary homological stability ranges. Okay. So how do you do this? The idea is that this will be a small cellular E2 algebra. So in spaces, if you want to build an approximation to a space, what you could do, at least in a range, what you could do is try and build one by attaching a few cells together in a way that captures the homology. Attaching cells is just some push out of disks along spheres, and you can make sense of that also in the category of E2 algebras. So the idea is that by taking some push outs of free E2 algebras on disks or spheres, you are going to try and build an approximation of the algebra you're interested in. So maybe it's going to look like free E2 algebra on a sphere to free E2 algebra on a disk. Now, there's two things you need to know. You need to know how many of these cells you need to get a good approximation. Let's call them E2 cells. Okay, there is some translation of this to some operatic homology theories, but in the end, this ends up again being the connectivity of some semi-simplicial set. So in that sense, this being the crucial input is not so different from the ordinary stability argument. And then you need to know how to deduce ordinary or secondary stability. And the crucial input here is that Fred Cohen computed the homology of free E2 algebras. With field coefficients. So in terms of certain homology operations, called Dirichlet operations in outer brackets. So at this point, you have an approximation which captures the homological stability properties of the thing you're interested in a range. And it's built out of a small number of cells. And you know what the homology is of each of these. So now it's a matter of doing a computation in this small model to deduce these homological stability or secondary homological stability results. Okay. So there's quite a bit of interesting homotopy theory going on in the first, well, maybe in all of these steps, where you're mimicking a number of constructions that you're used to doing in topological spaces. You're mimicking them in the category of E2 algebras, which is one of these more higher categorical settings you might be interested in. So that was our strategy for proving this secondary stability result for epic class groups. Okay, so these are the two more novel stability phenomena I wanted to talk about. They were representation stability, in the case that there's no homological stability, because there's naturally a group present that still acts, which increases in size, or higher order stability, which is about what happens in a metastable range past the stable range, and which, as far as I know, tends to involve some higher categorical structures. Okay, that's it for this mini-series. Thank you for your attention, and feel free to email me any questions you have. And I recommend trying the notes, the exercises in the notes, because some of them are pretty fun.
Okay, let's first of all thank him, as usual. You can unmute yourself or use your icons. And questions for Sander today?
Could I ask you about the result of Cohen very quickly?
Yeah.
So in this situation, you have, your functor that sends, I suppose, a space to the free E2 algebra on it. And what he did was compute the homology of this in terms of the homology of the original space.
Yes.
Because I just know the case of configuration spaces, but.
Oh, but the free EK algebra on a space
right.
is the configuration space of points
right.
with labels in that space.
Right. Sorry. Of course. Right.
Yeah.
And in your point 3, that you say need to know which E2 cells are required. I mean, this free E2 algebra that you construct is like not minimal in some sense, in that you look in the composables, you have some superfluous generators in homology. Is that what you need to be careful about 3? Like the Quillen homology, you need to compute it.
Yeah, so you want to build basically a minimal one, but you're not going to build one that perfectly approximates the one you're interested in. Here's what the idea is. You want to show that in a hypothetical which does exist minimal cellular approximation, you want to show that that doesn't require any cells below a certain line. So as G increases, you don't need cells of low dimension. And when you attach cells of high slope, which means that their dimension divided by G is large, they tend to only influence, in terms of whether stability holds or not, things on or above the same slope. So the important thing in building this small model is that it captures all the cells necessary below the slope you're interested in to build to have something. Well, there's only going to be finitely many cells below that slope, at least if the slope is at most 1, by that connectivity result of the semi-simplicial set.
Mm-hmm.
And then you just need to find exactly which ones you need to get the same homology as the the additional union of the classifying space of mapping class groups.
And I suppose
In that little region.
And there's where you need to exactly the size of the homology of a free one, I suppose, to bound the size.
You need that, so you need to know, like, if I'm adding a cell, how different, what's the answer I'm going to get out, and what do I need to fix up, maybe by more cells to get a good approximation to the mapping class groups. But you also need it in step 4, because step 4 is just doing a computation in this custom cellular E2 algebra A. And you just have to see whether there is homological stability or secondary stability or some other phenomenon happening there.
Right.
Like, so you're somehow agnostic before step 4 about what is even true in terms of stability. That's only at that point that you figure it out.
And could I ask about phi? So you said that map is not unique, but
yeah,
is there some property of the map that at least is, that is preserved? Like you're saying you can build it in different ways, and so
no, it's there's a, so if you were to invert 12 in Z, then it becomes unique.
So there's some torsion
and
ambiguity.
The subtlety is that this map doesn't come from, like, it doesn't arise from directly from the E2 algebra structure, because it can only exist after you've passed to taking the quotient by stabilization, so pass to these relative groups. And so it ends up being constructed by obstruction theory. And there's no obstruction to it existing, but there is an indeterminacy.
Okay.
And maybe there's a preferred choice, but we weren't able to, like, figure out whether there was a preserved choice, so we just dealt with any of them. The argument works for any of them, and for all of them gives
right.
them.
So for all of them, you have representation stability in that. Sorry,
for all of them, we have secondary stability. Yes.
Secondary, right.
Okay. Yeah.
So is this secondary stabilization map, is it related to the kind of, so Michael Weiss has this orthogonal calculus. So for example, if you look at pseudoisotopy theory and stabilization from the pseudoisotopy space, let's say P of M of a manifold to P of M cross an interval. So the fiber of that stabilization map also admits kind of a secondary stabilization. So if the fiber is F of M, then it has a map to loops of F of M cross I believe, which I think is constructible using this orthogonal calculus.
Yes.
So is there, and my memory is that that's kind of a structure where you get a fairly well-defined map. Is this as, so it's similar, but somewhat question, different.
Which I've had before. So yes, you're correct that ideally what you would want is some theorem that says on these objects, some structure that's present automatically builds for you, once you pass through the co-fiber of stabilization, builds for you what the secondary stability map is supposed to be, and then you prove something about it. And maybe a theorem like that exists, but I'm not aware of it. So in the examples that I know, you end up building these secondary stability maps by hand.
So I wonder if it might be related to the difference between symmetric spectra and orthogonal spectra, since his construction seems to be one about orthogonal calculus. So, so you know that this category Fi of finite sets and injective functions, it used to be called just I when Böckstedt worked on it in the 80s. So these functors from I were I spaces and so on. And the point is, if you take a symmetric spectrum and look at the underlying infinite loop space, then it's an I space. That's kind of how you go from symmetric sequences to I spaces by passing to the underlying infinite loop space. Whereas if you instead start with orthogonal spectra, the underlying infinite loop space of an orthogonal spectrum would be also a kind of I space, but now I is the category of inner product spaces and isometric embeddings instead. So I think that's much closer to the sort of, so it seems like maybe the Michael Weiss's orthogonal calculus is related to stabilizations that you would have when things are not indexed by symmetric groups and permutations or finite sets and injections, but by maybe orthogonal groups and inclusions of inner product spaces. So this perspective is developed in some papers by Christian Schlichterl and Stefan Segabe, for example. This interaction between symmetric spectra and I spaces and how that generalizes to other kinds of structured spectra.
I mean, I don't see any inner product spaces easily present in this example.
That's yeah, no, sure.
But I think it is a good question. I think what's somewhat unsatisfactory maybe at the moment is the fact that these maps have to be constructed by hand through obstruction theory. And maybe it is better to have some kind of calculus or other perspective that produces them for you.
Yeah. I mean,
this stuff is still developing, so I don't.
Right. Yeah. No, it might just be that the pseudo-isotopy space example is probably closer to one where there is a. I mean, when you have various, I mean, that's probably closer to inner product spaces or.
Oh yeah.
And so some of that, there might be some structure that's present for orthogonal spectra, and I think we're calling them W spaces rather than symmetric spectra and Fi spaces or Fi spaces, which might explain why the extra structure is present there. But it could easily be that the kind of prolongation from this kind of symmetric situation to the orthogonal situation would completely destroy any geometric interpretation. So, yeah. All right, thanks.
Yeah.
With these higher stability maps, you mentioned that they are kind of built by hand, but I'm curious, you know, so they're presented here on the level of homology. Do they exist on the level of spectra?
I think the answer is yes.
Okay.
Okay, other questions?
I have a question. So would it be possible to have secondary stability results without having primary stability results, or would that even make sense? Well,
I mean, in principle, yes. I don't know an example where that happens. Yeah, because I mean, it could very well be true that as a map like this, which is an isomorphism in a range, even though these groups never become zero in a range. I think that's possible. I just haven't seen that.
okay, thanks.
I would say that this way of proving it is maybe tricky because the input, this connectivity of these simplicial sets, it tends to also prove ordinary stability for you. So I don't really know how this type of argument would lead to that situation, but I could imagine it existing.
Another question?
One thing that one could imagine maybe, there is one quite strange example of a homological stability result, which I put in the references for the previous lecture, which is interesting because the stabilization map has the same domain as target, which is something you don't really expect. And so maybe as you would imagine, it's because this group has some kind of like infinite fractalness to it. So these are called Hickman-Thompson groups. It's a result of Marco Schimmick and Natalie Val. And maybe some kind of result like the one you suggest could appear in a situation like that, where there is a situation where the groups you're interested in have the stabilization map goes between the same groups somehow, because the group you're interested in has some kind of fractal nature to it. But I don't know an example off the top of my head where that would happen.
Thank you.
Anything else? Okay, if not, then we will wrap things up here.